In this video, we'll cover the concept of primitives in the context of the Qiskit IBM Runtime. This will likely be the last video in this series on how to use Qiskit version 1, but I will perhaps make an additional video just summarizing everything we covered. Now, I also plan to make this particular video as self-contained as possible so that those of you who are just trying to find a way to interface with Qiskit's hardware can follow along without having to watch the whole series. So let's go ahead and then just review what we've covered so far. We started by mentioning that there are different ways in which we can simulate circuits in Qiskit. We cover the quantum info module, which we use to simulate unitary evolutions of state vectors. Then we covered the basic simulator, which added the functionality of simulating circuits with mid-circuit measurements. We introduced the AerSimulator for noisy simulations and to use high-performance simulators for large circuits, and then discuss how the Qiskit IBM provider is being deprecated, so we can't use this traditional workflow to run our circuits in IBM's quantum hardware. We are now to use the Qiskit IBM Runtime, which requires this new concept of primitives. So in the last video, we introduced the primitives available within the Qiskit package, which are the state vector sampler and the state vector estimator. But we mentioned that these are tied to a particular backend, which is the state vector class, which has some limitations. We've also discussed how Qiskit Air has primitives, but unfortunately, because there are two different versions of primitives, version 1 and version 2, we were not going to cover these particular classes because they correspond to the old version, version 1, which are soon to be deprecated. We also mentioned that the primitives within the Qiskit package and the Qiskit Air package are tied to a specific backend, but the ones that belong to the Qiskit IBM Runtime package are not, and you need to supply that backend. Now, for that reason, the backend sampler and backend estimator were introduced also in the Qiskit package. But those are still version 1, so we didn't cover them. But we did mention that version 2 of these two classes is coming soon. Now, because these are not available as of yet, one thing that can be done is to actually use the primitives within the Qiskit IBM Runtime to run simulations. So what we're going to do in this video is cover the primitives within the Qiskit IBM Runtime module and explain how they can be used to both run simulations and execute on real hardware. So let me first give a quick justification of why the Qiskit IBM Runtime was introduced. So the typical way in which we would run circuits would be to first construct a quantum program in our local machine and then send a job to the quantum processing unit in the cloud, in this case to IBM's quantum processors. That job would, for example, get queued and then sent to the hardware for execution. Then the results will be sent back to our local machine where we'll get the number of, for example, counts of those experiments. Now, IBM introduced the concept of runtime because the previous model doesn't support certain type of programs that require both quantum and classical processing of information. So for example, if you're familiar with the variational quantum eigensolver program, where you have to execute a quantum circuit, get some classical results, and based on those results, change parameters of our quantum circuit and execute again. Doing that with the old model, we're required to send information back and forth between your local machine and the cloud, which has high latency. So with this new model, what we sent is not just the circuits to get executed, but a primitive job that would then be executed in the cloud in a more efficient way. The circuits will be sent to the quantum hardware. Interim results will be sent back to the classical processor so that parameters could be updated and sent back to the quantum processor, and the process will repeat until the whole program executes. Then the final results will be sent back to our local machine. So with this in mind, now let's start looking into an example of how do we interface with IBM's quantum hardware using Qiskit's IBM Runtime through the concept of primitives. So first of all, remember that we're going to be using sampler version 2 and the estimator version 2 in runtime. As I said before, it is really not worth wasting your time looking into the original versions of the sampler and the estimator because they will be soon deprecated. It is also important to remember that we need to have not only Qiskit installed, but also Qiskit Air and the Qiskit IBM Runtime package. Lastly, if you want to run your circuits in IBM's hardware, you need to have an IBM account and your token saved in your local machine. And you can do that with these two lines of code, where here you have to replace this text with your actual token, which you can get from the IBM Quantum website. All right, so first of all, we're going to do several imports here. We're basically first just going to import pi, which we're going to use for some parameters later on. Then from the Qiskit package, we're going to import quantum circuit class, quantum register, the classical register, and the transpile function. Then from Qiskit circuit, we will import the parameter class because we're going to use some parameterized circuits to make our examples a little bit more general. Similarly, we're going to import from the quantum info module the sparse poly operators so we can implement some observables. Then from Qiskit visualization, we're going to import the plot distribution just to display our results a little bit more nicely. From Qiskit Air, the AerSimulator, which we covered in a separate video. And then from Qiskit IBM Runtime, we're going to import the sampler version 2, the estimator version 2, which are the two main classes we're going to discuss. And then the Qiskit Runtime service, which is what is going to allow us to interface with IBM's hardware. All right, so with all those imports in place, the first thing we're going to do is to define our sampler instances. So first we're going to look just at the sampler. So as mentioned in a previous video, the sampler from the Qiskit IBM Runtime requires a backend to execute. So we're going to define two backends. One is going to be the AerSimulator, and then we're going to define a backend that corresponds to our quantum processing unit. And we do this by using the Qiskit Runtime service, and then we do get backend, and then specify the name of the one we want to use. So in this case, we're going to use IBM Osaka. With the backends once specified, we can then instantiate our sampler, and that's very simple. We just use the sampler version 2 class, and we specify which backend to use. One thing I forgot to mention is that in the case of the AerSimulator, as we discussed before, we could implement a noise model and pass it here in the definition of the backend to run a noisy simulation. The next step is to create our circuits. We're going to use two circuits in this example. One is a simple 1 qubit circuit, so it's just a Hadamard gate and a measurement. And the second one is slightly more complex. So we're going to have a parameterized circuit, and I'm going to use two parameters, theta and phi. And I'm also going to use a quantum register and a classical register in this circuit. So I'm just going to specify a quantum register with 2 qubits, and I'm just going to name it Q. And then for the classical register, it's also going to have 2 qubits, but I'm going to give it a random name. So I'm going to call this Koala, for example. And this will become important later on when we try to extract our results. Now I'm going to specify the circuit, which is going to look like this, an RX gate and a control RY gate, each of which is parameterized by theta and phi respectively. Now for the simulation, eventually we're going to have to specify the values of those angles. So I'm going to create a list for 3 possible values of these. So this is the format. So I have a list of lists where we pass the first value of theta, the first value of phi, the second value of theta, the second value of phi, and so on. Now one important question is, when we run the simulation, how is the sampler going to know which of these 2 parameters gets specified first? Well, if you're in doubt of what the right order is, one thing you can do is take your circuit instance and use this .parameters attribute, and that will give you the parameter view with the parameters in the right order in which they're going to get replaced once you run the simulation. The next step is to transpile our circuits to the corresponding basis gates of both the AerSimulator and the quantum processing unit respectively. In both cases, we're going to use the transpile function. So I just pass the first circuit and I specify the backend of the simulator. And then I repeat the same for that second circuit. Now, in most of Qiskit's current documentation, I've seen that the transpiling process is being done slightly different. So instead of using the transpile function, what I've been seeing is the use of this generate preset pass manager. And the process is a lot more complicated, but as you can see in these both cases, you get the same result. Reading the documentation, it says that this generate preset pass manager with the default settings does the same thing as the transpile function. So I think this gives you more flexibility, but in any case, for the purpose of this video, these two are perfectly equivalent. Now we're going to do the same thing for the quantum processor. So we're going to transpile now the first circuit using the Osaka backend, and we do the same for that second circuit we had. All right, so the next step is to execute our simulation. We saw this in a previous video, but I'll try to explain this again. So what we do is we take our sampler instance, in this case, the one for the simulator, and do .run. And then what we have to pass is a list of primitive unified blocks. And each of those primitive unified blocks corresponds to a circuit, a set of parameters, and since our first circuit has no parameters, we just pass none, and a number of shots. And then in the case of our second circuit, which is parameterized, we're passing that list of angles. So we're going to execute 3 separate circuits with 3 different angles, with a total number of shots of 1,000. Now for the quantum processor, we would do exactly the same. However, because this can take several hours to maybe even days, we're not gonna execute this right now. I already run this before and I have saved those results, which we can retrieve using the Qiskit runtime service. And then we do .job and then pass the job ID to retrieve those results. Now, if you recall, when we use the Qiskit IBM provider, the method that is used is actually called retrieve job. So this is slightly different, so keep that in mind. So now we have those results. We can go ahead and extract the number of counts because we're using the sampler, right? So remember, the way we do this is the result, and then we index the primitive unified block we want to access the results for. So in this case, it will be the first pub, which is this one right here. Then we do that data. Then we need to specify the name of the classical register where those results were stored. So for that first circuit, because we use the measure all function, it assigned the name of measure. And then we use the get counts method. So this is going to extract the results for the first pub that we executed. And then we can, for example, just plot the results to compare. So here we have the simulator versus what was actually executed on real hardware. We can do the exact same thing to extract the results for the second pub that was executed. So we index that with number 1. Now recall from the previous video that first we need to specify the name of the register. And because here I gave it the name koala, I need to do here .koala to extract those results. And the second thing to remember is that if we use here the get counts method, because this pub had more than one circuit, what it's going to do is sum up the results of all 3 circuits together. If we wanted to extract the result for an individual circuit, we will have to index it here in the get counts method. So this would extract the results only for that first circuit. And then we can compare the results, for example, by plotting them. We could change this to look at the second circuit or that third circuit. So that's pretty much it for the sampler. Now let's take a look at the estimator. So we're gonna go ahead and very similarly define the estimator instances. So this is almost identical to what we did for the sampler, except we use this estimator version 2 class. And we're doing it for the simulator and the quantum processor. Now, with the estimator, what we want to do is to calculate expectation values with respect to some observable. So we need to define that observable or list of observables. So here I have 3 separate observables. And one very important thing we need to do here is that because the circuits we're running only have 2 qubits, but the quantum processors might have a lot more qubits than just 2, we need to map these observables to the total number of qubits of the actual hardware. So I'm going to do this step by step here by first finding out what the layout of the transpile circuit looks like for the quantum processor using this .layout attribute. And then I'm going to iterate over this list of observables with a for loop, where I'm going to now create an empty list where I'm going to store the observables once they have been mapped to the actual hardware. I'm going to use this apply layout method on each of the observables in that list and then just append it to my new list. So all this is doing is adding a bunch of identities for the qubits that are not part of my circuit, but are there in real hardware. So this first item corresponds to this XX up here. It's just it added a bunch of identities, and same for this IY item where it just added the rest of identities. The next step is to run our simulation, and we do it in the exact same way we did it with the sampler. We just use the .run method, and we pass that list of primitive unified blocks, which for the estimator has a different format. So we pass the circuit, the list of observables, which in this case I'm just passing the original list because this is for the simulator, the list of angles that we're going to use in this parameterized circuit, and then the precision. And notice here, I'm just going to run one circuit for this particular example, not both of the circuits as we did for the sampler. Now, again, for the quantum processor, you would do this in the exact same way, but I'm not going to run this because it takes a long time, but I already have the results, which I'm going to extract in the exact same way I did before by using this .job method and passing the job ID. And once I have those results, I can just use the job.result, index the first result for the first pub, and here we only have one, .data.evs, which stands for expectation values. And then we can print that, and this is what we get for the simulator. So 3 lists, each with 3 separate results. So each of the lists corresponds to the results to each of the observables. And the values within each list correspond to the expectation value calculated for each of the different circuits that had different parameter values. And then for actual hardware, we do it in the exact same way. So that covers the way we would execute jobs in IBM's quantum hardware using the Qiskit IBM Runtime interface. Now, you might start wondering, well, what's the point of all of this? This seems almost identical to what we would do with the IBM provider. We're generating a list of circuits and maybe some observables, but the classical processing of all of this could be just done locally and then just send the list of circuits individually. And that is entirely true. The thing is that this is not the only way in which we can execute quantum programs within the Qiskit IBM Runtime. There are actually 3 ways in which we can execute these programs. First is the one we just covered, which is we generate a list of primitive unified blocks, send them to the quantum hardware, and simply receive the results. But there's also the concept of session, which is what we would use if we're running, for example, the variational quantum eigensolver algorithm, where what we have is parts of a program that have some classical computation and some quantum computation. So for example, imagine we classically define some parameters, run a quantum circuit, then send that to a cost function that would update those parameters, and then send them back to our quantum circuit that needs to be now executed in hardware. So all of this will happen in the cloud, both the classical and the quantum processing of information. And the idea is that when we establish this session, the system allocates the time for us to use the quantum hardware in combination with the classical processing without having to communicate back with our personal computer. Now there's a third way, which is called batch execution, which is somewhat similar to a session, but where instead of having quantum programs that depend on the result of a previous execution of a circuit, we just have a series of circuits whose quantum portion can be executed in parallel with, for example, some classical processing. So there could be some amount of overlap between the processing of a previous circuit with the execution of the next circuit. Now, to show how this works, I want to introduce another concept we haven't discussed before, and is that of a fake provider. So a fake provider is a backend that you can run locally that mimics an actual quantum processor. So it has some of the noise characteristics of those processors. So you can use them to try to get an idea of how your results will look like without having to use actual hardware. So we're going to look at an example of using a session. So for that, we import from Qiskit IBM Runtime a session. And here in this case, I'm using this fake provider called Fake Manila, which is a retired quantum processor that is no longer available, but there's a fake version of it that we can still use. Now we define a backend instance for Fake Manila, and then we can transpile our circuit using that provider. And here you can see that this one has a total of 5 qubits. And again, we need to map our list of observables to this new layout of 5 qubits because our observables are only for 2 qubits. And here I'm just using a list comprehension to do the exact same thing I did before. But here we can see the same observables where we just added these additional identities for the idle qubits. And then to execute within a session, we can use what is known as a context manager in Python. So the way we do this is by using with session, and then we specify the backend we want to use. Now, because we're using a fake provider, here we only need to specify the backend. If we were running in real hardware, we'll have to also specify a service, and we use the Qiskit IBM Runtime service in that case. But here, because we're only doing it locally, we don't need to do this, but just keep this in mind if you're actually running a hardware. And the context manager is going to create a session and then close it once everything inside of it gets executed. So for this example, all I'm going to do is just run the sampler for this circuit in the fake backend and subsequently run the estimator for the same circuit. So if we were sending this to a real QPU, all of this will be sent to be run in the cloud, versus if we do this outside of a session, then you would get on the queue to run the sampler, get the results, and then when you execute the estimator separately, you will have to get on the queue again to get your results. Whereas here, with the session, they will run consecutively within a single time slot. Now, when I execute this, I get a warning saying that the session is not supported locally when we're using the simulator. So all this is telling me is that the session has been ignored, but this is still the right way we should be doing this if we want to, for example, make sure our code is working correctly before executing a session on real quantum hardware, so we don't later find a mistake and waste all that quantum processing time that is very valuable. So in any case, ignoring the warning we got, here we got the results for the first circuit when we executed the sampler, which is what I had asked the code to return, and then the expectation value for that circuit. So that pretty much covers everything I wanted to discuss in this series of videos. I hope you found them helpful, and if you have any questions, let me know and I'll try to clarify to the best of my ability. Thanks so much for watching.